This is my lecture video specifically on rotational inertia and also briefly discussing Newton's second law of motion for rotational motion. So let's start. Recall that Newton's second law of motion states that an acceleration of an object is directly proportional to the net force. So if the force goes up, the net force goes up, the acceleration goes up, and inversely proportional to the mass of the object. So if the mass goes up, acceleration goes down, hence inversely proportional. Similarly, when an object experiences a net torque, so we have a net torque here, the object will experience an angular acceleration. We just finished equilibrium, and that's when an object has a zero net torque. This is what happens when there is a non-zero net torque. The angular acceleration is directly proportional to the net torque. So if the net torque goes up, the angular acceleration goes up, and is inversely proportional to its rotational inertia. I like to think of it as rotational mass. We're going to get into what that is, how to calculate it, and how it impacts the angular acceleration of the object. How this is written here is how it is on the AP equation sheet for both of them. But you are very much familiar with seeing it as the sum of all the forces, which is the net force is equal to mass times acceleration, and sum of all the torques is equal to the rotational inertia, think of it as rotational mass, times its angular acceleration. So you should be able to see the similarities between Newton's second law applied to linear motion and applied to rotational motion. So let's get into what is rotational inertia and how do we calculate it. But I'm going to talk about linear land first. This will help you understand it. Linear quantities. There is such a quantity as and the object's inertia. It is a unitless quantity. There are no units for inertia. It is the tendency for an object to continue to remain at rest or remain in motion. Okay, so that's something to do with Newton's first law. And then we have mass, which I will call it inertial mass. It is the actual quantitative measure of the inertia of the object. So inertia is a unitless item, and mass is the quantitative measurement of the inertia of an object. Mass is measured in kilograms, and that should make sense to you. Now let's talk about what that means. The inertia in linear system is an easier concept to understand. The more mass an object has, the more it tends to remain at rest or remain at motion, and the more force that it's required to change the motion. In a linear system, inertia depends only on the mass and not the location of the mass within the object. So if we have a box that has some dumbbells inside the box sitting on the ground and we want to accelerate that box at 5 meters per second squared, for example, we have to put a certain force on that box. And it doesn't matter that all the mass is located basically at the bottom of the box because the dumbbells are very heavy and they're in the bottom. That force will not change based on where those dumbbells are located within the box. Now let's talk about how these relate to rotational quantities. So rotational inertia, similar to the inertia of an object, is the tendency for rotating objects to remain at rest or to continue rotating. And the moment of inertia, given the symbol I, is the quantitative measure, back up, the rotational inertia is unitless. The moment of inertia is the quantitative measure of the rotational inertia of the object. So how much rotational inertia does the object have? The moment of inertia is measured in kilograms meters squared. Okay, now note, AP will refer to this as rotational inertia. They don't call it moment of inertia. They will tell you in a problem that the rotational inertia of the object is 4 kilogram meters squared. Um, I feel like they're incorrect in how they describe that because by definition, there are no units of rotational inertia. It's a unitless quantity. Moment of inertia is the quantitative measure of an object's rotational inertia. Very confusing, I know. Spent some time doing some reading back in the day when I first started teaching AP Physics and had to really think about this. I'm getting better, but at the same time, I want you to think of I as an object's rotational mass. So just like we have mass everywhere in linear equations, we will have rotational mass, and we will replace m with an I. So yes, rotational inertia is somewhat more complicated. An object's rotational inertia, that is, its tendency to continue moving at a constant angular speed, depends on its mass as well as the location of the mass, the distance of that mass from the axis of rotation. Therefore, the location of the mass matters. So we can't just know the mass of the object, we have to know where the mass is relative to what? The axis of rotation. Okay. The equation for moment of inertia is the sum of all the masses times the sum of them all the masses times those individual masses distance away from the axis of rotation squared. So there are an infinite number of masses potentially. So I could have I equals m1 r1 squared plus m2 r2 squared plus dot 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 dot, and I can go on forever. So the sum of all the masses times those individual masses distance away from the axis of rotation squared. Therefore, the units for in SI are kilogram meter squared. Now, because we don't want to deal with infinite number of masses, there is a simplification of this. So listen to this. A point mass is the simplification that assumes that the entire mass exists at a single point, which will simplify that equation above to I equals mr squared. Let me give you an example of what that might look like. So let's pretend that I'm holding a string. I'll call it a light string. And at the end of the string is a rubber stopper. And that has some distance away from that axis of rotation. And this has some mass. We're going to assume for a point mass that that rubber stopper's mass is located exactly at a single point. So we're not going to break it up into infinite number of masses. We will just calculate the I, or the rotational inertia of that rubber stopper using mr squared. Okay, so just reviewing, m in that equation is the mass of the object in kilograms, r is the distance away in meters, the mass is located away from the axis of rotation. If I have a point mass, I will only have one term in that equation, and it will be mr squared, one mass. If I have 3 point masses, then I'm going to have 3 terms in that equation. So the I value for a system containing 3 point masses will be m1 r1 squared plus m2 r2 squared plus m3 r3 squared. Shapes that cannot be broken up into um, point masses, such as the hammer that we talked about in the previous lecture, they have an infinite number of point masses and an infinite number of terms in that equation for I. Okay, so we'll talk about how to deal with that in just a minute. A system of objects, rotational inertia, can be found by adding up individual I values about the axis of rotation. Just like a system, the mass of a system will equal mass 1 plus mass 2, mass 3, if I have 3 objects in the system. So I values can be, we can add them, just like I can add mass, okay? Moving on. So let's do some examples. Let's calculate, using my rubber stopper as an example, the rotational inertia. Again, from this point forward, I'm going to refer to I as, I'm going to refer to I as the rotational inertia because that's how AP exams refer to it, and I don't want to confuse you. Even though technically this is the moment of inertia of a point mass. But I will use the same terminology that AP uses. So calculating the rotational inertia of a single point mass. That's what this first example is. So assume a 20 gram rubber stopper is at the end of a string of negligible mass, so I can ignore the mass of the string, and is swinging about a circle with a radius of 30 centimeters. And the mass of the rubber stopper is 20 grams. Determine the rotational inertia of the rubber stopper. So we're going to assume this is a point mass. It is going to equal mass times r squared. We need to convert the mass to kilograms, so I need to divide by 1,000, so that'll be 0.02 kilograms. We need to convert the radius to meters, so the radius in meters, I need to divide by 100, will be 0.3 meters. And so I will get a rotational inertia for that rubber stopper as 0.02 kilograms times 0.3 meters squared, which will equal, I have it somewhere in here. There it is. 0.0018. And what are the units? Mass times distance squared. And this is the rotational inertia of that point mass. Okay. Next, calculate the rotational inertia with multiple point masses. That's this example. How many point masses does this example have? I got 1, 2, 3, 4. Let's continue the question. Determine the rotational inertia of a majorette's baton made up of 4 balls fastened to the end of very light rods as shown in the figure. In other words, I can ignore the mass of the rod. Now we need to know where this axis of rotation is because I can spin this in multiple different ways. Assume that the baton is twirled about an axis perpendicular to the page, passing through the point where the rods cross. So if you could imagine, this is right here, I could actually put my pencil right on top of that dot, and that will be the point in which it spins about. And I can see that they've provided a little arrow to show me which way it's spinning. So we're going to calculate the I value for this system. And how many point masses do I have? I have 4. So I'm going to calculate I for the first one, I for the second one, I for the third one, I for the fourth one, and we will add them together, and that will be the rotational inertia of the baton. Okay, so all of the values were given to me in kilograms. And notice that the distance away from the axis of rotation is 0.5 meters for each baton end. So the I1 is 0.2 kilograms times 0.5 meters squared. I2 is 0.3 kilograms times 0.5 meters squared, plus I3, which is 0.2 kilograms times 0.5 meters squared, plus I4 is 0.3 kilograms times 0.5 meters squared. If we add all those up, we will find the I for the baton to equal, didn't spell that right, 0.2625 kilograms meters squared. Now I'm going to add another section to this question. If a net torque of 4 Newton meters were applied to the baton, what would the angular acceleration be? Okay, so Newton's second law applied to rotational motion is the sum of the torques, or the net torque, is equal to the rotational inertia times the angular acceleration. The angular acceleration is equal to the net torque. The sum of the torques and the net torque are the same thing, divided by its rotational mass. I was told 4 Newton meters was the net torque, and the rotational inertia for this is 0.2625 kilograms meters squared. And that will be equal to 15.2 radians per second squared. Now I want to do a unit analysis for you over here. I'm going to look at this Newton meters. By the way, I used all the proper SI units. I know angular acceleration should be radians per second, so it's going to come out to radians per second, but I'm going to prove it to you. So I have a Newton times a meter, and I have to break up what's inside a Newton. A Newton is a kilogram meter per second squared. If you forget that, remember your F equals ma. There's a kilogram meters per second squared. I still have a meter on top, and then I'm going to divide that by a kilogram meter squared, and you will notice that my meters cancel, my kilograms cancel, and I am left with nothing on top and second squared on bottom. And if you recall, radians are unitless, so we have to fill in radians. Oops, sorry about that. Now, let's talk about other objects that are not as simple as a bunch of point masses. Calculating rotational inertia for extended objects. The method used for calculating moments of inertia, remember what AP calls it. They will call it rotational inertia, even though I think they're wrong. In the examples above is simple when only a few objects rotate about an axis. However, when an object is an extended object, such as a sphere, a cylinder, a cone, techniques of calculus are required. Good news for you is that this is beyond the scope of AP Physics 1. You will not be required to do that. On the AP Physics exam, you will either be given an equation for the object's rotational inertia on the exam, or actually provided the value, where they will state the rotational inertia of the object about this axis is whatever in kilogram meters squared. So below are common shapes, however, that we will have to understand how their I values compare to each other. First is a hoop, which is shown here about the center of the axis. So this hoop is rotating as if I have a rod going through the middle and it's spinning about that rod. And notice the I value of this hoop. There's nothing. Its interior is empty. Is equal to mr squared. So it's almost like point masses. Like all the mass is located exactly as a point mass on the edge of that hoop. And let me see. So we call this a hoop, and hoop is equal to mr squared, the I value. Okay. A solid disk or a cylinder, and we'll call this they will refer to this. There's lots of these on the AP exam, an I of a disk. And notice that it has mass all the way through, so it's solid, is 1/2 mr squared. Now notice it's less than the I of a hoop. So if you have a hoop and a disk that are identical in total mass, the actual rotational inertia of the disk is half that of the hoop. In other words, it takes less torque to angularly accelerate the disk compared to the hoop. And why is that? Well, because there is more mass closer to the axis of rotation as compared to the hoop. And the closer to the axis of rotation the mass is located, the easier it is to accelerate or deaccelerate or change the rotational motion of that object. So then we'll look at a sphere. This is a solid sphere. This is 2/5 mr squared. And then we have a hollow sphere, 2/3. Let's compare 2/5 to 2/3. 2/5 is smaller than 2/3. 2/3 is greater than a half. 2/5 is less than a half. So once again, 2/5 is smaller than 2/3. And why is that? Because it's a solid sphere, more mass is located towards the axis of rotation than in a hollow sphere, which is 2/3 mr squared. Now, the axis of rotation matters. So here is a thin rod. The I value of a thin rod when there is an axis of rotation through the center of the rod. Let's get that to go away. I don't understand what it's doing. Oh, there we go. Yeah, we have, why is it doing that? I don't understand why it's doing that. Try it again. We have an axis right here. There we go. Okay, so I'm spinning it about the center. So I'm rotating as it's shown. And notice what the I value is, 1/12 ml squared. But I could have the axis located here. And so now the rod is going to spin about the end of the rod. And notice that the I value is larger, 1/3 is larger than a 12th. Why is that? Well, because there's more mass farther away when it is spun about its axis located at the end of the rod. So you're not going to be required to have all of these equations memorized. I personally think you should know by heart the I value equations for hoop and a disc, but you will be required to understand how the mass location affects the object's tendency to have resist change in its angular motion. Okay, so let me show you an example of what I mean by that. We have two rigid objects shown. We have a disc and a hoop. They both have the same mass. So we'll assume that this is M and this is M. This is considered a disc and this is considered a hoop. All the mass is located at the edge on the hoop, and all the mass is evenly distributed about the disc for the disc. Okay. If the same, and they're spinning about an axis of rotation right through the center, excuse me, that matters. So here's the axis of rotation, here's the axis of rotation. If the same braking torque is applied to each, which will take longer to stop? Explain your answer. Well, torque net is equal to times acceleration. Acceleration is equal to net torque divided by I. The disc has 1/2 mr squared. The hoop has an I value of mr squared. Okay. So the I value for the hoop is larger than the I value for the disc. Therefore, the acceleration of the disc is less than, maybe I'll do this, is less than, come on, the acceleration of the hoop. I'm sorry, Miss Curry reversed that. Let me do it again. The acceleration is proportional to the net torque, which is going to be the same number for both of them, and inversely proportional to the rotational inertia. So the acceleration, so which one's larger? Which rotational inertia is larger? The hoop has the larger rotational inertia. It is located in the denominator. So if the larger the I, the smaller the angular acceleration. So the angular acceleration of the hoop is less than the angular acceleration of the disk because more mass is located away from the axis of rotation. Well, they asked for which one takes the longest to stop. Well, based on our equations, we started at the same angular speed. So angular final equals angular speed initial plus angular acceleration times time. Time is equal to the angular speed final minus the angular speed initial divided by the alpha, the angular acceleration. We know both of them comes to a stop. The acceleration is going to be negative, so we'll get a positive time value. The initial angular speed is the same for both. And now we can answer the question about time. Since the hoop angular acceleration is less than, then we know that the time will be greater than. So the time for the hoop to stop is greater than the time for the disk to come to a stop because its rotational mass for the hoop is greater than the rotational inertia of the disk. Okay. All right, one last problem and then I'm done. Actually, that's not true. I got to fill in some blanks. They want to know which one will get to the bottom of the ramp first. What will be the order? We're starting from rest and we're going down the same ramp. I have a solid cylinder. I have a hollow cylinder, a hollow sphere, and a solid sphere. They all have identical mass and identical radii, and they're going to be released from rest. And so I'm going to go through and look at my equations for all of the items here. We have um, a cylinder, a sphere, a thin. So we're going to write the fractions for each one of those. So we have the solid cylinder. Well, how about I just draw it like this? The solid cylinder is going to have 1/2 mr squared. The hollow cylinder is just going to have 1 mr squared, so I'm just going to put a 1. The hollow sphere is going to have 2/3, and the solid sphere is going to have 2/5. So now, which one will get to the bottom first? The one that is easier to accelerate down the ramp will make it to the bottom first. The acceleration is inversely proportional to its rotational inertia. So once again, the one that is easier to accelerate, the one that has the greatest acceleration, will get to the bottom first. So that I value needs to be the smallest, and the smallest I value will be the 2/5. And then we will have two, I'm sorry, 1/2. Then we'll have the 2/3, and then we're going to have the last one, which is the 4th. And that will take the longest to get there. So this is first place, second place, third place, fourth place. All right. That's the kind of questions you're going to have to be able to answer. Rotational inertia is the resistance in change to angular motion. Inertia is the resistance to change in linear motion. The more mass that's concentrated near the axis of rotation, the smaller the rotational inertia is. And the lower the rotational inertia is, the easier it is to change the angular motion. That concludes my lecture.